All right, hi everybody. We're going to try this. We are going to see if we can't do a screen recording of our lecture on acid-base interactions. Now, the first part about this is to make sure that we know what happens when two solutions are added together. They're going to dilute each other. By the way, if you'd like to follow along here, we are in the Schoology page here, and all I have done is I'm going to live cast the lecture notes section so you can follow along if you would like with the textbook section. I am in textbook section number 11, acid-base interactions strong here. I'm just going to walk through some of the problems that are here. So if you want to export this to Notability and follow along with that, that's great. Or you can follow along with what I've got here on the Notability. So what's going to happen here is in each of these problems, you're going to add two solutions together. Now what we're going to be doing is we're going to be doing acids and bases. But for right now, let's just make sure that we're clear on what's going to happen when we add solution A and solution B together. Eventually, A and B will be our acid and base. So let's just say for the sake of argument that I have solution A, which is 100 milliliters of 0.5 molar, and solution B, which is also 100 milliliters of 0.5 molar. So there's solution A and there's solution B. So remember, what's going to happen is that solution A and solution B are going to be mixed together. And instead of being 100 milliliters of each, they're now going to be 200 milliliters of each. So from an individual standpoint, A went from 100 to 200, and B also went from 100 to 200. Now, the long form of this is that we are going to have M1V1 equals M2V2. Or we are going to have 0.5 molarity of A that we started with at 100 milliliters, and that's going to go to X molarity at 200 milliliters. But if we rearrangeify all of this, we are going to get that X molarity is going to be 100/200ths of 0.5 molarity, which makes sense because it's going to be half of the 0.5 molarity. So my new molarity is going to be 0.25 molarity. That's there because it went from 100 to 200. Not surprisingly, B is going to be doing the exact same thing because B is also 100 milliliters here, and it was also 0.5 molarity that was there. So for solution B, if I just cut to the chase, the new molarity for B is going to be, again, 100/200ths, because that's where I started right here, and that's where I ended right here. So it's going to be cut by those two factors, 100/200ths of the 0.5 molarity that's there. So the B is also going to end up being 0.25 molarity. Now this one was easy because everything started off the same and the numbers were nice and round that's there. What if the numbers aren't so nice and neat, and what if the numbers aren't so nice and round? Well, let's look at a couple of other problems here. Example 1, solution A is, it says it's 100 milliliters of 0.4, and solution B is 50 milliliters of 0.25. What's going to happen when they mix together? Now, of course, all of this assumes that they are going to mix together and there's going to be no loss of volume, which is what's going to happen, 99.9% of the time. But solution A, basically what it's going to come down to is that it is going to be diluted by a factor of 100/150ths. Why is that? Because, again, you're adding 100 to 50. And so for the A, it is going to end up being 100/150ths because we are adding the two solutions together of 0.4 molarity. And B is going to be the same thing, except it's only going to be 50/150ths of 0.25 molarity. So if we continue with this process and just end up doing the math on this, then what we end up with is the math turns out to be 0.267 for the first one, molarity, and the math on the second one turns out to be 0.0833 molarity for that one, right? Sometimes these numbers can get really weird and wonky, but ultimately it's the same process. So we'll do one more. Example 2 here says solution A is 57 milliliters of 2.3 molarity is mixed with solution B, which is 38 milliliters of 1.9 molarity. Again, because reasons, for whatever reason, they decided to mix these two solutions together. What are the new concentrations going to be? Well, solution A is going to be 57, except now it's going to be 57 out of the total. And the 57 is going to get added with the 38. So the 57 and the 38 go together to be 95. So that's 57 95ths, whatever that turns out to be, of 2.3 molarity. And solution B is going to be the same thing, but from its perspective, which is going to be 38 95ths of the 1.9 molarity that it started with. So they will again cross-dilute each other and end up with different concentrations. And so the A is going to end up at 1.38 molarity and the B is going to end up at 0.76 molarity. So that's our first step here, making sure that when you add two solutions together that you remember to dilute them before you do anything else. Alright, so now what we're going to do is we're going to see what happens when a strong acid and a strong base get together. Now there's a couple of different ways that this can end up. You could end up with more acid than base, you could end up with more base than acid, or you could end up with the same. We're going to start with the first easy one where they end up the same. If you have a strong acid and a strong base that go together, clearly what we've learned before is that you're going to get a double replacement, or a neutralization reaction occurs where you are going to get water and salt out of the equation. So for example, the classic example of this is if you have hydrochloric acid that is going to be reacted with sodium hydroxide, then you're going to get water out of it, H2O, and salt, NaCl. Now this is easy because we know that hydrochloric acid is one of our strong acids, so it goes 100% of the way. And we also know that sodium hydroxide is a strong base, so it goes 100% of the way. So we can be assured that when these two guys get together and go over here to the right-hand side, that all of the hydrochloric acid that can react, reacts, and all of the sodium hydroxide that can react, reacts, and you end up with 100% of the way over here on the right-hand side, which means that you just end up with some salt water over here. Now, it's probably not a shock that if the only thing that we end up with is salt water, that our pH is going to be 7. Let's kind of prove that one time so that we never have to prove it again. So let's take a look here at this guy. This one here says that we have 50 milliliters of 0.2 molar hydrochloric acid and 50 milliliters of 0.2 molar sodium hydroxide. So just a casual observation of it should indicate to you that the answer to this is going to be 7, because you have the same amount of our acid as you have of the base here. But let's go through it long form one time just to provify it. So our first one here is going to be the acid. Remember from our previous lesson that when we add these two things together, these two solutions together, they cross-dilute each other. So my acid is going to end up being not 0.2 molar, but it's going to be something less because it's going to be diluted. How much less? Well, remember that it's going to be 50 milliliters here added with 50 milliliters here. So from my acid's perspective, it's going to be 50 100ths, because the two 50s go together to make 100th. And it's going to be 50 100ths, or half of 0.2 molarity, or my acid is going to be 0.1 molarity. Turns out that the base is going to be the same because the base is also 50 molarity. But we now have 100 milliliters, 50 milliliters I should say, and then we now have 100 milliliters total. And that is going to dilute the 0.2 molarity that it started with as being 0.1 molarity. So now what's going to happen, if we again do this out the long way, we're going to have HCl plus NaOH is going to come over here to make H2O and NaCl. And I got an I and I got a C and I got an E like normal, right? Except that my acid is going to be 0.1 and my base is going to be 0.1, and who cares what the water is, and I don't have any salt to begin with. But we have learned that this is going to go 100% of the way over to the right-hand side because it's a strong, strong situation. So how far can it go? Well, they're equal, so it can go 0.1. So I can lose 0.1 and be left with no acid, and I can lose 0.1 and be left with no base. And not that I really care, but I'm going to gain 0.1 molarity of the sodium chloride and end up here with 0.1 molarity of the sodium chloride. But I have no acid and no base left over here. Now, technically speaking, that's not true. Technically speaking, I do have some acid and base left because, again, I can't be zeros here. Now, how much is it? Well, the only thing I have left in this situation is now water. So, remember, if I have pure water left in the beaker, because really that's all it is, because salt is not going to do anything to it, then the water is going to break up according to the autoionization of water reaction at 1 times 10 to the negative 14th, which is my kW. And now we've done this one before. We have some water that we don't care about. We have technically none and none. We're going to lose x, and we're going to gain x, and we're going to gain x to be x and x. Or x squared is going to be 1 times 10 to the negative 14th, or x is going to be 1 times 10 to the negative 7th, which means if I take the negative log of that, I'm going to get a pH of 7 and a pOH of 7, which again is our neutral situation. So the point of this is that if you have a strong acid, strong base interaction, and it happens to be at the equivalence point, in other words, you end up with no acid left over, no base left over, then what you are going to end up seeing is you are going to end up seeing that you're going to end up with a pH of 7 because technically they can't be 0. So if you end up at this point where we were before, where you have nothing of one and nothing of the other, it's technically not 0. But if you end up there, you can safely assume that you have a neutral, and your answer is going to be a pH or a pOH of 7, assuming, again, you're under normal circumstances, 25 degrees Celsius, where the kW is 1 times 10 to the negative 14th. Now, this one, again, was obvious, I think, because it was 50 milliliters of 0.2 molar strong acid and 50 milliliters of 0.2 molar strong base. They could provide you the same information, except maybe not necessarily as obvious. So let's look at example 4 here. Example 4 is going to turn out to be the exact same problem. It's just not quite as obvious necessarily. So what have I got here? I have got 20 milliliters of 0.5 molar nitric acid, and I have got 40 milliliters of 0.25 molar sodium hydroxide. What is the pH of the resulting solution? Well, in order to do this, once again, what we have to do is we have to cross-dilute each of these guys. So my strong acid here is going to be 20/60ths. Again, where does the 60 come from? The 60 comes from the fact that I have 20 and 40 that are now being added together. So the 20/60ths is going to be my dilution factor. So it's going to be 20/60ths of 0.5 molarity for my acid. And then my base here is going to be 40/60ths of its starting concentration, which is 0.25 molarity. So again, the 60 here comes from the fact that it's 40 and 20 together for our 60. Again, and the 0.25 molarity for the base is from the fact that we have the 0.25 there. So once we end up diluting these guys by the appropriate amount, we end up then with 20/60ths of 0.5 molarity, which is going to be 0.167 molarity. And lo and behold, 40/60ths of 0.25 molarity is also 0.167 molarity. And nobody wants me to go through that same problem I just showed you. Suffice it to say that I have equal amounts of strong acid. That's my strong acid. And equal amounts of strong base. So, because I have equal amounts of strong acid and strong base, they are going to completely neutralize each other, and you are going to be left with none in your overall solution, which is technically not true. You're going to end up with 1 times 10 to the negative 7th. So again, if you set up an ice table, of HNO3 plus NaOH comes over here to form water, and NaNO3 with an I, a C, and an E, and you have 0.167 and 0.167 here, and who cares about the water and none of that. It's going to go over 100% of the way because it's a strong, and you are going to lose 0.167 to be left with none. You are going to lose 0.167 to be left with none. You are technically going to gain 0.167 because I suppose they could ask you about what the resulting concentration of the sodium nitrate is, and it would be 0.167 over here in this particular example. And again, technically speaking, this answer here is not true. This is not real. It's not technically 0 and 0. It is technically 1 times 10 to the negative 7th because it's in neutral water, and 1 times 10 to the negative 7th. So it's a pH, and it's a pOH of 7. So my pH here is 7, and my pOH here is also 7. So at first glance, this did not seem to be at the equivalence point, but upon further investigation, once we cross-diluted them, it turned out that I had the same amount of strong acid and strong base, and so that is going to be at the equivalence point, or I'm going to end up at a pH of 7 there. One more example here that's, again, even weirder, but we're going to end up in the same spot. Please recognize here that I have 10 milliliters of 0.8 molar sulfuric acid, and I have 40 milliliters of 0.4 molar potassium hydroxide. This one here is technically a little bit weird because what part of the sulfuric acid do we care about? We care about the acid part of it, and remember, the sulfuric acid was one of our weird diprotic ones. So in reality, the 0.8 molarity of the sulfuric acid is really 1.6 molarity of the hydrogen, because there are 2 hydrogens there, and it is considered to be strong diprotic, so it double dissociates there. So technically speaking, our solution here, when we go to dilute these guys for the acid, because again, what you're going to do is you're going to have 10 and 40 that are added together. So our acid is going to end up being 10/50ths of 1.6 molarity of the acid, because again, you have to double it because it's diprotic. And as far as our base is concerned, you're going to end up with 40/50ths of 0.4 molarity. And by the time you end up doing 10/50ths of 1.6 molarity and 40/50ths of 0.4 molarity, assuming my mathification is correct, you are going to end up with 0.32 molarity here, and you're going to end up with 0.32 molarity here. So you are going to end up with the same amount of the strong acid as you have of the strong base. So 0.32 molarity of the strong base and 0.32 molarity of the strong acid. You are going to end up with a pH of 7 because that is at the equivalence point. So if you react solutions together, strong and strong that is, and you end up with the same amount of each, you are going to end up with a pH of 7 at the equivalence point. All right, almost done here. So what we have seen is that first, when we combine 2 solutions together, we have to make sure we dilute them. Second, when we combine a strong acid and a strong base, they react completely. And if they happen to be at the same amount after they are diluted, then your pH is going to be 7. What's going to happen, however, if we combine 2 solutions and dilute them, and the strong acid is more than the strong base, or the strong base is more than the strong acid? Well, one of them is going to then be in excess, and we'll be able to figure out what the pH is based upon our pH square. So let's take a look at this. We are on example 7 now from those lecture notes. And so what we've got here is we have got a strong acid, 50 milliliters of 0.3 molar hydrochloric acid that we are going to mix with 50 milliliters of 0.5 molarity sodium hydroxide. So obviously, the first thing that we have to do is dilutify them. So I've got my strong acid and my strong base that's here. Remember that they are going to be 50 and 50. So they are going to be 50 100ths, or they're going to be cut in half, or if I do it the long way, then this guy is going to be 50 100ths of 0.3 molarity of my acid, and this guy is going to be 50 100ths of 0.15 molarity of my base. So once we end up doing the math on that, this guy ends up being 0.15 molar, and this guy ends up being 0.075 molarity. All right, so now let's walk through what happens when we combine them. We have the HCl and we have the NaOH, and we are going to combine them to make water and sodium chloride over here. I got an I, I got a C, and I got an E here. And it looks like my red acid here is 0.15, and my blue base over here is 0.075. And who cares about the water, and ultimately who cares about the salt, although again they could ask you about this. Now, we know that this reaction is going to go 100% of the way all the way over, but now we're in a curious spot. And that spot is a limiting reagent problem, because it's going to go all the way that it can, but it can't go completely all the way over because we have more of one than the other. And it really appears that we're only going to be able to lose 0.075 to be left with none of the base, because we have more of the acid over here, which means that after we end up doing the math on that, the 0.15 minus the 0.075 is going to be left with 0.075. So now it appears that we have 0.075 molarity of the excess of the acid. So if it just wants to know what the pH is, so now all we have to do is take the negative log of the remainder. So now I'm going to take the negative log of the remaining 0.075, and I'm going to end up with a pH of 1.12. That's there, right? Now, technically speaking, again, this is a lie right here, this 0, because you can't be at equilibrium and be a 0. But remember from our pH square that if you know any one of the four corners, you know all of the four corners. So if I have H positive and OH negative, and then over here I have pH and POH. If I know that my H is 0.075 and my pH is 1.12, that means that my POH is going to be 14 minus that. So that is going to be 1288 that's here. And then my OH negative is going to be 10 to the negative 1288. Or I could have calculated the concentration of the OH negative by dividing it into 1 times 10 to the negative 14. So if I get my calculator out here, sorry about that. Here I go. So this is going to be 10 to the negative 12.88. So that's going to be 1.3. 2 times 10 to the negative 13th. So technically speaking, that's not 0. That is a value of 1.32 times 10 to the negative 13th. But for all intents and purposes, that is 0 that's there. But the point is that with these reactions, you are going to have an excess of one of the other. You react it all the way, and if all they want to know is what the pH is, then all you do is take whichever one is left over, take the negative log of it, and that will give you the appropriate p-value for that, be it pH or POH. So all they wanted to know in this one was that the pH was, and so this is a 1.12. Let's take a look at our next problem here. Our next problem is I've got 20 milliliters of 0.0048 molar hydroiodic acid that's there, and apparently I have 42 milliliters of 0.0094 molar lithium hydroxide, which again, weird numbers, but whatever, we can play whatever game that they would like to play. Remember, when you react these guys together, you're now going to have 20 and 42, so that's going to be a total of 62 milliliters when they are reacted together. So our first task for our red, at any rate, is to take 20/62 of 0048 molarity, and so that's going to get us 00155 of our strong acid, and our base is going to be 42/62 of its molarity, which is the 0094 molarity that's there. So our base is going to end up at 00637 molarity that's there. So in the instant that they are combined and diluted, but before they react, they are now the 00155 and the 00637 that's here for this guy. Sorry, that's a 7 for those concentrations. Then they're going to react as far as they can. And what do I have? I've got HI plus lithium hydroxide, both strong species. So we're going to go to water and lithium iodide over here. I got an I, I got a C, and I got an E, and who cares about the water? And I got 00155 here, and I got 00637 here. And again, nobody cares about the lithium iodide unless that's the point of the problem, but it's not. So this is now going to react over as far as it can. It's pretty obvious that my red acid is the limiting reagent here, so I'm going to lose 00155 to be left with 0, although that's technically a lie. It's just going to be an extremely small number. And so if I take my 637 and subtract the 00155 from it, I am going to end up with 00482 that's there. And again, please keep in mind that I now have excess of my base. So if I take the negative log of 00482, I'm going to end up with a pOH value of about 2.32. And if I'm interested, however, in the pH, I just subtract that from 14, and I get a pH value of 1168. That's there. So again, all you are doing is you are taking the solutions, you are cross-diluting them like we did to begin with, you are then reacting them as far over as you can possibly react them, and then taking the leftover of the solutions and going from there. This also works if you have a diprotic situation. Just remember that in a diprotic situation, you have to multiply it by 2. So this one here, example 9, 40 milliliters of 0026 molar sulfuric acid. Remember that sulfuric acid is one of my diprotics. So because of that, that's really not 0026, that's really 0052 because I'm interested in that. Other than that, the problem now continues just as we did before. I have 40 and I have 30, so my total is going to be 70. So far as my acid is concerned, I've got 40/70ths, and the 40/70ths is going to go with the 0052 molarity. So I am going to end up with 00298 molarity of the acid. And my base that I have here, right, I have 30 milliliters of the 0038 molar of the sodium hydroxide. So my base is going to be 30/70ths of 0038 molarity. And so I am going to end up with 00163 molarity of my base. Now that I have cross-diluted them and I have doubled my sulfuric acid because it's a diprotic, I can react these guys as far over as I can. So it's pretty obvious, I think, at this point that I have more acid than I have base. So I'm going to completely run out of my base, and I am going to lose 00163 of this guy. So I'm going to be left, as far as acid is concerned, with 00135 molarity of my acid that is left over. And so if I take the negative log of 00135, I end up with a pH of 2.87 is my pH that's there. So in all of these cases, we have now combined all of the skills that we have learned. If you take two solutions and dilute them together, you have to cross-dilute them by their volumes. You then react it as far over as you can. Whichever one you end up with more of, that one you take the negative log of, and it becomes the P of that value. So in this example, we ended up with excess acid. We took the negative log of it, and we ended up with the pH. In this example, we ended up with excess base. So the excess, you take the negative log of it, and you ended up with the POH, which you could then change back to pH. And in our last example here, we ended up with excess acid, and so because we ended up with excess acid, we take the negative log of it and end up with the pH value that is there.